So today we're going to go over a little review we did as the warm-up today because we're heading towards a test in radicals and rational exponents tomorrow. And basically, if you can do everything on this sheet, tomorrow's test should be pretty easy. Okay, the first question is pretty straightforward. You just want to change this from a radical form to an exponential notation, exponential exponent. And as you can see, there's no perfect cube root in 55, so that's all you can do with that. This one, too, is meant to be pretty easy. If you cube root a number and then you cube it right away, well, then those two operations cancel each other out. So that's all you can do with that. This one's a little more involved. You have to think of this as 1 over a to the 4/5. And then if you want to simplify it by one more step so that you have a single number instead of a rational expression, you can say that it's a to the negative 4/5. And the negative exponent is what makes it be a reciprocal. So there's the first three. Now these kinds of questions will ask you to do without your calculator. You should know that this means the same thing as the square root of 36. And that this one, you can do two ways. You can either square 64 and then cube root it. But wouldn't it be easier to cube root 64 first and then take that to the exponent of -2? Because the cube root of 64 is just 4, and 4 squared is 16, so 4 to the -2 is a 16th. This one here, again, you have to realize that you're square rooting both 9 and 16, so that's just 3/4. Okay, these guys. Now it says write an equivalent expression using exponents. So this is m to the 12, n to the 6, to the 1/3. Then this, of course, is square rooted, so that means to the 1/2. From there, I can combine these first, maybe it would be easier. So I'm looking at m to the 12, n to the 6, to the exponent 1/6. Remember, when you take the power of a power, you multiply those exponents. So this would be m squared n to the 1. This one over here, the 5th root means I'm taking it to the power of 1/5, but I'm also taking all of that to the power of 10. And if you multiply those exponents together, you get 2. So I'm looking at x cubed y all squared, which can be expanded to be x to the 6, y to the 2. This one throws in a little bit of an algebra wrinkle to it. So if we cross multiply here, we get root of 18 over root of 45 equals x. And think about that. The root of 18 and the root of 45 both have a square root of 9 in them. So they can both have a 3 come out of there. So the square root of 18 is 3 root 2. And the square root of 45 is 3 root 5. Those 3's cancel. So that gives me root 2 over root 5. But remember, we're not supposed to leave a radical in the denominator. So we're going to times that by 1. In this case, root 5 over root 5, so that we rationalize the denominator, giving us root 10 over 5. Another piece of algebra. The smart way to do this one is to realize that 81 is a power of 3. In fact, it's 3 to the 4, and that I can change this to a 3 being in the numerator if I consider that 3 to the -4. So if this base has that power and it equals the same base to this power, those two powers must equal each other. So then 2p must equal 1, so p must equal 1/2. This guy. Okay. It's kind of hard to tell where to stop when you simplify something like this. I'm going to just maybe do it one step at a time. If I square root 8, a 2 can come out of there. And if I think about 15, well, 15 has a perfect square in it times another number. So I'm going to take the perfect square of 14 out of there. See this, just to make sure you guys understand what I'm saying. Remember, you add those exponents together, right? And this is, any even power is a perfect square. So this is next to the 7, and then y to the 6 times the square root of, well, there's still a 2 because 8 is really 2 root 2. And remember that this x to the 1 would still be in here. So I think I'm going to maybe just leave it like that. I don't know that there's anything. Well, that's not true. I guess I can cube root these two things. So this 2 can't be cube rooted and get anything reasonable. But x to the 7 does have an x to the 6 times x. And x to the 6 is a perfect cube. It's x squared times x squared times x squared. So that means that this x to the 7 has an x squared that comes out. Y to the 6 is, of course, y squared when you cube root it. Then there's all the stuff that's still trapped in the cube root. Namely, there's still a 2, there's still an x, and then there's still a root 2x. Now, the argument can be made that that isn't really looking any simpler than the original statement was, but leaving it in radical form, that's as simple as it can get. Keep in mind, it didn't say in the question that it wanted you to stay in radical form. I had some students who approached this question by changing it to fractional exponents. So they had this, and then it would be square rooted, then cube rooted, which is to the power of 1/6. So they kind of left the question like this, which does simplify a little bit down to this. This would be, of course, 5 over, yeah, 3 goes into these two numbers, so that's 5, whoops. So that becomes 5 over 2, and then this just becomes 2. And I think if you were to write the answer in fractional exponent form, that's about as simple as you could make it. But again, the argument could be made that it's hard to look at these and say one's all that much simpler than the other. So questions like this very often end up in multiple choice form, where we could say, you know, this term here is equal to this, it's equal to this, give you 4 choices and find the one that it isn't equal to. So be aware that that might be the way we test that. More of the same. All right, I think this time I'm going to try to combine all these to single bases. So let's see. This would be x squared y to the power of a third times x y to the negative 1 to the power of negative 1/6. Okay, let's distribute this power first. So that's going to be the square root of x to the 2/3 y to the 1/3 times x to the negative 1/6 y to the positive 1/6, because a negative times a negative is a positive. From there, remember that when you multiply two exponents that are powers that have the same base, you can just add the exponents. So 2/3 plus negative 1/6 is like saying 4/6 minus a 6, which is 3/6, which is a half. And 1/3 plus 1/6 is like saying 2/6 plus 1/6, which is 3/6, which is also a half. So this ends up being x to the 1/2, y to the 1/2 to the 1/2, which I guess simplifies down to x to the 1/4, y to the 1/4. Or if you wanted the simplest form but radical, it's the 4th root of xy. Both of those would be the simplest way you could write the answers. Now on to working with radicals. All right, if we multiply these two guys out, we're going to get 15 root 60. Distributing that one, you're going to get minus 3 root 21 times 6 is 126. Better double check my mental math on that. All right, there is some perfect squares in here. 60 has a perfect square of 4 in it. So the 4 will jump out and make that a 30 because it'll be the square root of 4 is 2. And then root 15. Here, the perfect square in 126 is, I believe it's 9, right? Yep, there's a 9 in that number. So the 3 will actually become 3 times 3, making it a 9. And when I take a 9 out of 126, I'm going to get, let's see, 1 and 14. And that's as simple as I can make that. I can't combine these anymore. They're not alike terms. Next, this one, I'm going to have to rationalize my denominator here by multiplying by the conjugate of this denominator. And then I have to use my foiling skills. All right, this term times this term is 3 root 35. That's first times first. Outside times outside is 2 times 7. Inside times inside is 6 times 5. And last times last is 4 root 35. All right. While we're on the subject of the bottom, the reason we picked this conjugate is so that we didn't have any middle radical terms to deal with. So this is 3 root 5 times 3 root 5, which is 9 times 5, which is 45. 2 root 7 times 2 root 7 is 4 times 7, which is 28, the minus. All right, let's simplify the top. 3 root 35 plus 4 root 35 is 7 root 35. And this is 14 plus 30, which is 44, all over, did we have that right? 14 and 30, yep. And at the bottom, 45 minus 28, I think that's 17. And is there anything I can simplify there? Nope. That's the best I can do with that. And the last one, all right, remember how we square something? When it's a binomial, we square the first, we times the two together and we double it, and then we square the last. Here, these two are conjugates, so I don't have to worry about middle terms. I'm going to get 4 root 3 times 4 root 3, which is 16 times 3, which is 48. And 3 root 5 times 3 root 5, which is 9 times 5, which is 45. And they are difference of squares, so they're subtracted. So I'm going to get 5 plus 3 is 8, plus 2 root 15, minus 45 minus from 48 is 3. So I'm going to get 5 plus 2 root 15. And that's the little review we did today.